let's continue then to see how all this applies to robots. And we'll take again an easy example of this planar robot that we worked so far. Let's try to calculate basically the Lagrangian of this system. All right? Because if we have the Lagrangian, then we can do the derivation and we end up with equations of motion that we'll see later on how we use for control. So just to understand what's going on here, we have these two joints, Q1 and Q2, and each one of these links have masses. Right? We haven't talked about masses so far because kinematics we don't talk about masses, but now we need to know things about masses because we saw that the kinetic, potential, energy depend on masses. Right? We have no mass, we don't have energy. Right. In general, that's again a simplistic approach, but for the lab and for our course, we typically assume that the mass is in the middle of the link. Right? All the mass is concentrated at the center of the link. All the mass is here. So we don't model any densities and so on. Say, okay, the mass is here, and that's it. We have basically a point mass. All right? It doesn't have to be like this, but for simplicity, we do it like this. Right. We need to calculate the Lagrangian, and we said that we express the Lagrangian in generalized coordinates. I kept on using this letter Q, so probably you see where it's going. But basically, yeah, we could describe the Lagrangian in terms of x and y coordinates. That would imply calculating the coordinates of the masses in x, y. So we have the kinetic energy as a function of x, y dot, and so on, or polar, or whatever other coordinates. But basically, the most convenient way of describing the system is using the joint coordinates, right? Q1 and Q2. Why do you think is that? I'll explain because it's maybe too far-fetched, but you saw here when I did the derivation, basically I put the inputs at those coordinates, at those degrees of freedoms, right? I want to have equations of motions where the input is the inputs at my joint, so basically joint torques for revolute joints or joint forces for prismatic. And I want to have an output that joint accelerations, which is basically then I can use to calculate forward kinematics, velocities, and so on, right? And in the end, the state of my robot can be fully described by the joint coordinates, by where the angles, how they are rotated or translated, and how fast they're moving. Right, so very important when I calculate the Lagrangian of a robot system, I describe the Lagrangian as a function of its joint positions, joint velocities, which means the potential and kinetic energy has to be as a function of joint position and joint velocities. Right. Now, in the first example, we talked about a simple mass moving up and down and rotating, but we had just one mass. Now we have a system with two masses, right? This complicates things a tiny bit. Basically, we need to calculate again the overall potential energy of the system, but that's basically the sum of the potentials of the two masses, right? So, of each segment. Right, what is the potential of each segment, of each link? We don't care about the potential of the link, we care about the potential of the mass, because that's basically, we consider the whole link is concentrated at that center of mass, right? So this mass 1. So what is the potential of this mass? And let's write it down. So this would be my V1. And let's take a reference, where the red line is at the joint level. What is the potential of that mass? M1G and some height.
1/2 times sine of Q1
All right, let's draw it here so we see it. Have the mass, we have L1, we have this angle Q1, and this is M1. And basically we want to find this length, right, this height. Right, this is has 1, whatever. I could say has 1 here, but we said that we want the Lagrangian. Let's write it explicitly here. We want this to be a function of Q and Q dot, right? So I need to express the kinetic and potential energy as a function of Q and Q dot, right? So I could say has 1, but this is not a function of Q and Q dot, right? So I need to rewrite this as a function of that. And your colleague said that it's basically this height is this length, L1 over 2. It's half because we said that the mass is at the middle of the link. All right? Sine of Q1, right? And now this is a function of Q1 or Q. Okay? Here when I say Q and Q dot, Q, as we discussed previously, is basically a vector of all the joint coordinates, and Q dot will be all the joint velocities. Great, so that's the first mass. What about the second one? So now I have another link, another mass, M2, another joint Q2, this is L2. I need now this height. So this is M1, M2, G has 2, which is what? Again, I need has 2 as a function of Q, which will be Q1 and Q2.
It will be the L1 over 2 sine of Q1 plus.
So you say this height is split in this height, right, and this height. This height is L1 sinus Q1. Let's write it here. M2G is L1 sinus of Q1, right, this part, plus this part. How much is this part?
Sinus of L2 sine of Q2.
And I'll use this notation we used in the past, S2 equals sinus of Q2, because I don't have space. Great.
Should it be M1 times G times L1?
This one? Why L1?
No, M1. M1.
Should that be an M1?
Yeah, I put it here and I forgot it there. Good point. Yes. So we see here that V2 is actually a function of Q1 and Q2, or overall of Q, right? Great. So the overall potential energy will be the sum of the two. So let's see here, V2 is this form. Ah, sorry. This is not Q2. My bad. Because Q2 is just this part. But I need this whole angle. Right? This is Q1. So this is 1, 2. Yes. Thank you, slides. Right. Easy to get carried away. Great. So if this is the potential of the second mass, then the overall potential will be what? We'll have this form. M1G L1 over 2 sinus of Q1 plus M2G, this whole term. Or if I want to describe it in terms of forward kinematics, I corrected the slides, but it seems they didn't make it to production. This should be T. This is the transformation matrix from origin to respective mass. right? Mi. So this is M1, M2, which is the third row, fourth column. This is in Python, so we start from 0. So third row, fourth column will be what? X, X, Y, X, Z, X, P, X, P, Y, P, Z, 1, 0, 0, 0, and here the other terms. It's basically this element. If I assume that Z is pointing upwards, of course. So basically, by doing the forward kinematics until this mass, and until this mass, I can take the position of the coordinate frame attached here on the Z direction, or whatever direction is pointing upwards, negative to gravity. Yeah, I just thought of writing it in a more condensed form. That's the general way of calculating it, right? Because here, this will depend on the design of the robot, how the axes are rotated. But I can calculate it for any robot if I know the forward kinematics, which we know how to calculate by taking the forward kinematics until the center of masses, and then taking the coordinate along the gravity direction. Typically, we put Z pointing upwards, so this would be this element, all right? So in the general way, it's like this. Clear? Here I wrote V, Q, and Q dot as a function because I want the Lagrangian to be Q and Q dot. Does V depend on Q dot? It does not. And typically, potential does not depend on velocity. It just has to do with positions, stresses, deformations, whatever, positions, not velocities. So this is typically a function of Q. But that's fine. I mean, no depends on Q dot. Doesn't mean that I don't have it there. All right. Good. Potential energy is there. Let's talk about kinetic energy. Again, the kinetic energy of this system will be the kinetic energy of this mass plus the kinetic energy of this mass. Right? So I take T1 and T2, I add them together. So let's start with kinetic energy first for the first link. What form will I have here? T1 linear, Q and Q dot. Basically, I want to calculate, sorry, just to explain here, I want to calculate what? The linear velocity of this mass. That's what I need, right? Let's say this rotates like this. I will have some linear velocity as a vector here. So what do you want to say?
M1 times
M1, 1 over 2, M1.
times U.
This vector transpose this vector, right? What is that vector?
Would it be Q1 dot over L over the L1 over 2?
So in this case, for this velocity, U1, the vector or the?
Let's go scalar.
Let's go scalar. The magnitude of the vector, all right? Would be what?
Q1 dot
Q1 dot, so how fast the angular rotation here
over L1 over 2.
over,
I was thinking of converting from angular velocity to linear velocity.
right? And the form is times r. This is meters, this is 1 over second, so this is meters over second. Right, so this is times L1 over 2. All right? We'll get back to vectors in a second. How do I calculate the angular velocity, the linear velocity of this one?
Similarly, but now
taking in calculus so U1,
Sorry?
taking to take in account also U1.
Q1 as well.
Q1.
Q1 dot, sorry, yeah.
We have to calculate the distance from the
This would be I will have basically two contributions, one due to this joint and one due to this joint, right? The linear velocity due to this joint will be q1 dot times this distance. And then the other one will be the angular velocity of this one times this distance, right? Do these things sound familiar? All right. And another thing to maybe familiarize more. Let's say I don't want the norm. I want the vector. How do I do this with the vectors? Well, how did we write this in vector form? Cross product, right? Where did we encounter these cross products and whatnot, distances, moments of arm, linear velocities, and so on? The Jacobian, right? So what I'm trying to do is calculate the linear velocity of these masses as a function of the joint velocities, right? This is exactly what we did at the Jacobian, right? We did it for the end effector, but we can say that the end effector is here. I then calculate the Jacobian until mass 1. Calculate Jacobian until mass 2, right? This is stuff we know and we can use. For simple case, it might seem easier to just calculate what's the linear velocity here. But you see, when I start going to the second joint, things start adding up, gets more complicated, and eventually I go down to calculating the Jacobian again by calculating cross products, the difference of the end effector minus the origin of the joint, and so on. So overall, I want to calculate this. So the sum of all the masses times their velocities. But I want to calculate this as a function of q and q dot, and that's basically what the Jacobian does for me, right? So I can substitute this thing here, u1 vector, this is the linear part of the velocity, with the linear Jacobian times q1 dot, correct? Let's put the 1 here. If we know how to calculate the Jacobian, we can, substitute. Let's see how I have it here. What Jacobian? Yes, that's an important thing. So let me make some room here. And expand a little bit on this one. So here I have the total kinetic linear energy is 1 over 2 sum from I1 to N UI T MI. This is I UI. And these are vectors. Okay, so for our case with the two masses, it's 1 over 2 U1 T M1 U1 plus 1 over 2 U2 M2 U2 and transpose here, right? And I say I can substitute this U1 with the Jacobian, so I can write 1 over 2. And also an interesting, useful thing that we need to know, the transpose, let's write it here. The transpose of this is what? Is Q transpose J transpose, right? So I change the order and I transpose things. All right, so here I will have Q1 dot, this is a scalar so I don't have to transpose, and I have GU1 dot M1 GU1 Q1 dot, right? So here I have to do this transposition, here I don't have to, plus Q2, here I have Q1 and Q2 as a vector because maybe before I go there. And we'll see why we have a vector here. So here, what Jacobian am I calculating? We saw the Jacobian, as I say, for the end effector, where it gives me the velocity of the end effector as a function of joint coordinates. But now I'm trying to calculate the velocity of this mass. So I need to calculate the Jacobian as if my end effector was here. Right? So it's a Jacobian until mass 1. Right? This Jacobian, the velocity will depend on what velocities? Does it depend on this velocity? Yes. Does it depend on this velocity? No. Right? This comes afterwards. How this moves doesn't affect the velocity of this one, right? You can do whatever you want. Right. That's why here I just have Q1 with this Jacobian. Great. So now if I go to the second Jacobian, I have to calculate. I'm trying to calculate this mass, correct? And this mass, you said very well that it depends both on the velocity of Q1 and of the velocity of Q2. Right? So here I have basically now, sorry, my Q is a vector, so I will have Q1, Q2 dot Jacobian of U2, M2, Jacobian of U2, Q1, Q2 dots. Here it's transposed, here it's not, because here it's transposed, so, right? All right? Good. So I need to calculate, basically, in this case, two Jacobians, one until mass 1 and one until mass 2. Yes?
The second Jacobian, should it also be 1 over 2?
Yes, this should be a 1 over 2, or you can put a bracket here. Easier. It doesn't fit there. Yes. Good. So we calculate this Jacobian until mass 1 and mass 2. So if you remember, we have this linear Jacobian, which is the cross product between the axis of rotation and the distance from the joint until the end effector. Now my end effector, I put it there OM1 because my end effector is mass 1. So mass 1 minus O1, so this vector. And for the second one, it will be mass 2, 0, 1 on the left and mass 2, 0, 2 on the right. All right? So these two Jacobians are not the same Jacobians. They're similar in a way, but they're not the same. Right. So that's the first thing we need to discuss. The second thing is about dimensions. What is the dimension of this Jacobian if it is until mass 1? JU1. 6 by 1. Why?
Because we have the position of the transition, 6 because we have 6 degrees of freedom, and 1 because we have only one joint.
One joint, right? So the second part is correct, the first not. But the logic is fine, right? So we're only until here, so we have only one joint involved, so we have just one column. It's 3 by 1 because it's the linear Jacobian, it's not the angular Jacobian. So we would just have the linear velocity part, right? It's half of the Jacobian. That's why. But the logic is there. That's what the difficult part is realizing that this is a one column one, right? What about this one? The Jacobian until here. So JU.
It will be 3 times 3.
3 times 3?
We have
Times
two
2?
joints that are coming.
There are two joints until here, right? So we have basically two columns. Sorry. 3 times 2. All right? Great. Now we'll do a small trick just to be able to combine these things a bit nicer, and we assume that here we still have Q2 dot and Q2 dot, so we can factor these things out. Because if we can do this, then we can factor this out, and it makes a bit nicer our equations. But then if this is a 3 by 1, transposed it will be actually a 1 by 3, and this is a 1 by 2, I cannot multiply them anymore. So what I do is I basically add one extra line of zeros here, so I make it a 3 by 2, and then this a 2 by 3, and then this will be a 3 by 2 times 2 by 1, so that I can basically have the same sizes for Q and the Jacobians, right? Since I put 0 here, everything that gets multiplied with Q dot on this Jacobian will have 0 effect. So I can keep the same dimensions for these Jacobians and these Q's, and I still don't add any effect for Q2 here because the effect will be 0.
So
because
we add zeros just to ensure equal dimensions.
Yes.
It does, you really from the DAG or something like that, or it's a mathematical explanation.
there is explanation that the effect of Q2 on a velocity of mass 1 is 0. So you can also see it like this. Because that's what the Jacobian tells me, right? What's the contribution of this velocity on the end effector velocity, and in this case the end effector is mass 1, the contribution is 0. So I can add it.
Yeah.
Right? That's the explanation. But it's convenient if it's the same size, because I can basically rewrite this equation, I can rewrite it in a very compact form as 1 over 2 Q transpose dot sum of the Jacobians Q dot. All right? Because I can factor out these ones now, because they have the same size. And I can also put this in the same sum because the Jacobians have the same size as well. They're filled with zeros, many of them, but they have the same size, and then I can add them together. All right? Good. So this is basically the overall kinetic energy, the linear kinetic energy for any robot manipulator. What do we need in order to calculate it? What appears there? Joint velocities, which we are controlling, and it's our states. And, sorry? The masses. Joint positions. Why? Very correct. That comes next, but yeah, very correct. So Jacobian is a function of Q, if you remember. And basically the Jacobian, which in order to calculate the Jacobian, we needed forward kinematics, dH, and that's it. So if I know forward kinematics, that's all I need to calculate kinetic energy in this formulation, right? You're not impressed.
We are first learners.
All right, good. What about the angular kinetic energy? Thinking similarly and generalizing, I'm not going into details, but again, instead of having linear velocities here, I will have angular velocities. So T angular sum omega I omega I, and this is transposed for Nandor, as you were about to complain. Right, so now I have angular velocities. How do I calculate angular velocities as a function of Q and Q dot? Again, angular velocities of now, it's not the masses, because now I don't have point masses, because point masses don't have angular momentum, but it's of the whole link. How do I calculate the angular velocity as a function of joint velocities? The Jacobian, the other Jacobian, right? I can use omega I the angular Jacobian times q dot. I can substitute here. I'm not going again to the same explanation, but it's the same logic, exactly the same logic. I have linear velocity, I use the linear Jacobian at the masses to calculate it. The same thing for angular velocities, for angular kinetic energy. I use the Jacobian to calculate the angular velocity, right? Why did we have to bother figuring out the Jacobian? All right. Again, I have to do the padding, so the dimensions of the Jacobians are the same and the Q's are the same, but eventually I will end up with a similar form. One little detail here for the moments of inertia, and it's why I wanted you to understand a little bit what the moments of inertia are about. These moments of inertia, this I, they're expressed on a frame attached on the link itself. Like we have an object, we know, the inertia in a frame attached somewhere in the object, right? We need to transform that into the reference frame of the robot, because eventually these links we will need to calculate their kinetic energy with respect to, a reference frame, the same reference frame, right? So I need to basically do a transformation where I use the orientation matrix for that link. So this is R0Mi is the orientation part of the transformation for that link with respect to the base frame. I do this operation so that I transform the moments of inertia from its own frame to the reference frame. It has to do with the actual rotation. So the moments of inertia will tell me that this thing has some inertia when it rotates around this axis, but I care how it is around this axis, basically. And this thing, again, we know how to calculate from forward kinematics. I do the forward kinematics until that link, I know the orientation, and that's it. So if I take all these things into consideration, I basically can rewrite the angular velocity in this form, which is similar to this form, where instead of linear kinetic energy, I have angular kinetic energy, and instead of linear Jacobian, I have angular Jacobian, and instead of masses, I have the moments of inertia transformed in the reference frame. But you see again, Q and Q dot get factored out. Sorry, Q dot and Q dot transpose get factored out. So when I'm trying to calculate the total kinetic energy, I'll take the sum of these two. And again, I'll factor out Q dot, because again, it's common on both the linear and the angular part. And I can write the whole kinetic energy in a very compact form, as you see it here. Right? And this is general, like there's nothing specific to this robot here. This equation works for any robot, as long as we can calculate the Jacobian, which means we can calculate the forward kinematics. So that's all I need. I need the forward kinematics, basically, to calculate the Jacobian, to calculate the dynamic model.
I have a question. Could you repeat, please, why we use Jacobian to go to the joint angle to the 0.5?
So we want to calculate the kinetic energy of the system, right? That basically boils down to calculating the velocities of the masses of the system, linear and angular velocity, right? That's what the Jacobian does. That's one thing. The other thing is that we want the Lagrangian as a function of Q and Q dot. That's our states of the system. Joint position, joint velocities, right? So I need to bring these two together. I need to describe the kinetic energy, which is velocities of the masses, as a function of Q and Q dot, right? And the relationship is the Jacobian, because the Jacobian tells me what will be the linear velocity of the masses as a function of joint velocities and joint position. Good question. All right. Does kinetic energy depend on, it depends on Q dot, right? It has Q dot there. Does it depend on Q? On position? You said it already. Where does position Q come into play? what part here depends on Q? The Jacobian, right? You remember the Jacobian is a function of Q. The Jacobian is used here. So, yeah. So, what does this tell me is that the kinetic energy of the system does not depend only on joint velocities, but it depends on joint positions as well. And let's try to visualize this. We have the system and it has some inertia when, let's say, this joint moves, right? I will have a different inertia, I don't know, if the robot is folded like this and then this joint moves. Right? The masses are more concentrated, so obviously the angular momentum is less. Right? The linear velocities of the links are smaller because I have less arms, basically. So then, for the same angular velocity, I will have more or less kinetic energy based on the joint configuration. So here I present an extreme case, but you get the picture. Like, okay, how come the joint position affects kinetic energy? Because we said kinetic energy is a function of mass and velocities. But basically joint position affects joint velocities. And effector velocities. Due to the Jacobian being a function of Q. Any questions? Right. Now let's see a little bit on dimensions, and I want to write a big equation here. So I'll erase these parts. Because we said earlier that the kinetic energy is what kind of quantity? Is it a vector or a scalar? A scalar, right? So does that produce a scalar? Because there I have a bunch of matrices, right? So let's do some dimension analysis. Q dot transposed. It's not dimension analysis, that's not the right term, but anyway. And Jacobian UI TMI Jacobian UI plus Jacobian omega I transpose orientation matrix until mass 1. This is the moment of inertia with respect to its own frame. Transpose J omega I Q dot. This is for n degrees of freedom, n joint robot, right? We see the example with 2, but as I say, this is the general form for any robot. What would be the size of Q dot for n joints? 1 over n? 1 times n, because it's transposed, right? Good. And then this will be n times 1. Great. The Jacobian here, this is I. Remember we said that we pad the Jacobian with zeros. The first Jacobian will pad it with as many zeros until we have n columns. The second one, the third to nth column will be zeros and so on. So basically all these Jacobians, they have the same size. Almost?
Oh, it's linear, 3.
Right, so this will be 3 by n, and this will be n by 3. This is scalar in this case, right? The angular Jacobian, the same thing, right? N by 3, 3 by n. What is the orientation matrices? 3 by 3. And the transpose 3 by 3. And moments of inertia, 3 by 3. So what's the result of all of this? This 3 by 3 with these 3 by 3s will be still a 3 by 3. This n by 3 times 3 by 3, n by 3 times 3 by n will be n by n. So this will be an n by n. This one also n by n. If I add, because this is a sum, right? If I can add them together, they're all the same dimensions, so I can add them together. That's why I had to pad the zeros, right? So I can add them together. So the result will be n by n, multiplied from the right by n by 1 times 1 by n. The result will be a scalar. Well, right. So kinetic energy is a scalar. That's correct. And it's a function of q and q dot, because we have q dots there and then we have q's in the Jacobians. So what is the sizes? Yeah, because we say we pad, eventually we will have this form here. Now, because this is we said that this is a m by n before I do the multiplication. This whole thing is basically a square matrix, n being the number of joints we have, right? And it will always be a matrix no matter what robot we have, unless we have one joint, then it's a scalar, bine, but it's still a matrix. So we typically write this whole thing as d, which is a function of q. This is just depends on q, doesn't depend on q dot, and we write it d. In some textbooks, it's written as m. For various reasons, I find this a bit complicated, because when you talk about the elements of m, m1, m2, and so on, it might get confusing with those m1s, which is not exactly the same. I use d, some people use m, right? So I can write the whole Lagrangian for any robot arm, basically, as a in this form, right? No matter how many joints, it can have 30 joints, we can still write it like this. That's it. And you see that in order to calculate d, all I need is the masses, the moments of inertia, the Jacobians, basically forward kinematics. The Jacobians is forward kinematics, this is forward kinematics, so the masses and forward kinematics. All right. Now, in order to get to dynamic model, which is differential equations, we need to do this derivation, right? This is not the end. We just have the Lagrangian, but we need differential equations with velocities and inputs. So I need to do this derivation. In order to prepare for this, let's expand a little bit. And basically we can see that this part here, we can rewrite it as it is on the screen as well. This will be 1 over 2, the sum of the individual elements of I and j. So this is basically vector, matrix vector. This is basically a sum, a weighted sum, right? Qi, Qj. Hello. Dij, this is a double sum from I to j until n, right? Where Dij is the ith, jth element of this matrix D. Okay? And the right part we keep the same. So the whole Jacobian is basically, the whole, Lagrangian is this sum of mass I, mi, 2, 3, I1 until n. This is the Lagrangian. All right. So let's derive. So let's calculate this. Now, Q is a vector, right? So I have to do a derivation for Q1, Q2, Q3, Q4, Qn, right? And I will get an equation for the motion of Q1 with the input of tau1, which is the torque at joint 1. Another equation for Q2, another equation for Q3. So I will have basically a system of equations, a system of differential equations, because each one of them is a differential equation. Right. we'll work as we worked before. We first derive with q dot. Right? If I derive here with q dot, and if I take just q1, let's say I fix one of these indices. Let's say this is 1. So this will always be 1, 1, 1, 1. What will I have? So this part does not depend on q dot, correct? So all this part will be 0. So the derivative with time here, if I take this as a sum, you can imagine, you know, all the end terms adding up here on the right, and I derive with q1, what will I have?
d11 times q1 dot.
Sorry?
Well, we have only one term in the sum.
No, because I fixed one here, but j keeps on running for all the joints. Right? So if I have two joints, it will be, let's say, 1 over 2 d1 1 q1 q1 plus 1 over 2 d1 2 q1 q2 dot. So what will I have? This is basically square.
It's d11 times q1 plus
d11 q1, so the 2's will go away. q1 dot plus, when I derive with q1,
only q1 will disappear and the other things will
q2, right? Correct? All right. Is this going where I want it to go? I'm not sure. Good. Let me write. So when I take these, yeah, I'll basically have this sum. It's not the same. What am I doing wrong here? So if I say k is 1, so I fix k, I have the sum. Or is the same thing here? Come on, wait a bit.
in this case. Do we have a q2?
Yes, we do. q2 dot. Let's say with this case with the two joints. I mean, it's the same for the other ones. 1 over 2. Sorry?
In the second part of the equation, the 1 over 2 disappears, and then it is the same.
Yeah, but why does it disappear?
Well, that's the question.
Yes, I know why. Because here we have 2, and we have also the other part. So we have another 1 over 2 for 2, 1. No, actually, sorry, this is still for all of them. Sorry, but we just derive with 1. Yeah, that's the mistake I'm doing, sorry. So this is this plus 1 over 2 d21 q2 dot q1 dot 1 over 2 d22 q2 dot, and I derive this with Q1. It's a mistake I'm doing, right? So if I derive this with Q1, I will have 2 times this thing, D11 Q1 dot, right? I will have 1 over 2 D12 Q2 dot, right? And another 1 over 2 D21 Q2 dot, right? And this will be 0 because I derive with Q1, right? D12 and D21, they're the same because they're diagonal. So I will have basically, yes, I will have D11 Q1 dot plus D12 Q2 dot, which is what we have on the screen. Yeah, I made a mistake here. I derived the whole sum. I just derived with Q1, but I still derive the whole quantity. All right, have to hurry up. If I derive this with time, what will I get? Now here is a little bit more complicated because both of these and these change with time. So it's a more complex derivative. I have basically, seeing it a bit simple, I'm almost done. I have, but there's no course here. There's nothing on the table. D being a function of Q, a function of time. So when I derive it with time, I basically take the derivative of the left side times the right side, plus the derivative of the right side times the left side. So that's what I have here. This is Q dot dot, the derivative of the right side, plus the derivative with time with the left side. This we keep in mind and come back later. And when I derive with, so this is this derivation. And when I derive with the right side, basically with Q, I have the potential coming into play. So this depends on Q, but also this depends on Q. It's too much to explain now in 2 minutes, but the idea is that we end up with this equation. The D matrix comes back, because when I derive here with Q dot and with time, basically I have the D matrix times Q dot dot. And I have a new matrix called C, Coriolis term, gets multiplied with velocities, and I have this vector G, which is a function of Q dot, of Q. And this is equal to the torques. So matrix D is the inertia of the system, C is the Coriolis terms, and G is the potential, the gravity matrix. This is how you calculate it. And the only thing to remember is basically that these are matrices and these are vectors, so this is a system of equations. We're not going to abandon this. We're going to use it next week again. So some more details we'll describe next week again, and in the lab to smaller extent this week, to more extent next week. So sorry for the last part being a bit rushed, but that was basically it. This describes the whole dynamics, and from now on we can talk about control, which we'll do next week. Questions? So we have external pressure.